is a general presentation because I want to stress out this, what we are facing now in Mexico, because it's a practical problem in which we have to deal with emerging pollutants. I will maybe skip the background because you already know, but more or less everybody in here, we are wanting to know how the transport and fate of pollutants can be inferred from properties and laboratory studies. While we are doing that, there are other practical problems. I'm going to bring you to Mexico, so we are going to take a flight to Mexico City. And first of all, you need to understand that Mexico City is placed on a closed basin at 2,240 meters above the sea level. As it was a closed basin, there was a need to open artificially the exit of all the wastewater, and it turns out that the exit of the wastewater goes into a valley that is placed north, called the Tula Valley, and all the wastewater from Mexico City is sent there. Mexico City has 21.4 million inhabitants, and thus it demands a lot of water, 7.4 million of meters cubic per day. As this is a very huge city, in Mexico we talk in meters cubic per second, so it's near 86 cubic meters per second. And we take all this water from the local groundwater, we imported also water from other basins, and we are doing reuse, a lot of reuse. We are doing planned reuse since 1956 to refill recreational lakes to irrigate green areas for car washing. A city with 21 million of inhabitants has 3 million of cars, so there is a lot of demand for water to wash the cars, so all is reused water for environmental restoration and also for industrial cooling. But still we need more water, and we are now thinking on reusing the wastewater for drinking purposes. All the water that is treated is being reused in the city, and that's amount 10% of the water. The rest of the water that is not treated is sent to the Tula Valley since 1896, the year 1886, and it has been reused for irrigation. Currently, 60 cubic meters per second of non-treated wastewater are being sent to this valley to irrigate 90,000 hectares. Why this is happening? Because the Tula Valley is very dry, the pluvial precipitation is of just 525 millimeters, and the evaporation rate is very high. The water is so important to farmers that they requested to the president to grant them, so the owners of Mexico City non-treated wastewater are the farmers, and a very complex irrigation system has been built there. Because of the wastewater presence, you can see, not very clear, but in the first photo you can see there was no soil in that area, but thanks to irrigation, now it is one of the, not only the biggest irrigated area in the world using wastewater, but is one of the most productive areas of Mexico City. Why? Because in wastewater you have organic matter and nutrients, and you have water all year round, so farmers can raise crops 3 to 4 times per year, and 1 hectare of land having access to wastewater is rented 2 to 3 times more than a piece of land that has no access to wastewater. So it has even an economic value. There are also health effects. I'm not going to go into the detail related to microorganisms. Only for you to know is that is in this area where WHO get the data needed to set the criteria to reuse water for agricultural irrigation. I will show you some photographs. This is the exit of Mexico City wastewater. You can see in there up to 300 meter cubics per second of wastewater. Is impressive. This is the way in which the wastewater is distributed into the canals. This is flood irrigation. This is furrow irrigation. And you can see here a valley a part of the valley where there is no access to wastewater is turned into this. In the middle is a river of wastewater. But as the wastewater is discharged into the agricultural fields, a part of it is recharging the aquifer, and in the land below of this area, there are several springs emerging. You can see here several springs. Water is being used for recreational area, and even this water is being bottled and sold as spring water. So, when this situation was perceived by the government in 1995, and I remember just now when we were seeing the analytical techniques, at that time the techniques for emerging pollutants were not available, and we were facing this problem. We began to make several studies. Our first study in 1995 was just to assess the quality of the water in that area, because there was 500,000 people drinking of these new wells. We used the current drinking water norms of Mexico, comprising 44 parameters, and we found that in general was very nice, but on some places where wells were drilled in the middle of agricultural fields. But as we saw that the problem was fecal coliforms, and we knew how to deal with them using chlorine, we thought that it was a good quality of water. Certainly, the first time you see this, you say this is not possible. We are using non-treated wastewater to irrigate. How comes the water is very good quality? So we performed a second study with 4 laboratories in parallel, 2 from the university, 1 laboratory certified in the United States, and we enlarged the number of parameters up to 288, taking parameters from WHO, from the parameters used by EPA, by the European Union. Once again, we found in general the water was very nice quality, but we began to observe some chromatographs peaks, and we began to say, well, there is something in this water that we are not dealing with because we are not measuring. We even managed to to calculate the removal efficiency by the soil, and it was similar to a tertiary advanced wastewater treatment plant. But still we saw these problems with some compounds that at that time we didn't have the proper methodology, and most of the compounds we were finding were below the detection limit. But while we were doing that, the government of Mexico City, because Mexico City is still growing, people were asking for more water. So the government had the idea that why not taking back this water from the aquifer to Mexico City instead of treating the wastewater in place. That, when you know about the emerging pollutants, you begin to have some sources of concerns. What thing could be best? Using wastewater treated on site for drinking purposes, or to take the water that goes to the Tula Valley, recharge the aquifer, takes a better quality, and bring it back to Mexico City. We did several studies, and then we began to say, well, we don't still have the analytical technique. Let's try to begin to remove all this peak on the chromatograms. In the first one, you can see the raw wastewater, and in the second, the chromatograms in different springs, and then after filtration. So we did a lot of work of that, and in parallel, we began to identify the flora and fauna on different new springs that were formed. But we were trying to measure the impact on aquatic biota. But as I mentioned at the beginning, this area was a desertic area, so in fact, there was not biota at the beginning. The biota was formed once the springs were formed, and we found that in general the ecosystem had representatives of several types of organisms, and it seemed very nice. We studied the percentage of female and male fishes and tried to find out if there was feminization on these fish. We didn't find any significant result. And we even found in the area a Mexican stream called Acosil that in general is considered as an indicator of good quality of water. We did a lot of studies using aims and different toxicology, mutagenicity tests and different tests. And in general, we find out that there were no major concerns, and when there was major, and in parallel, we managed to put in place a very good treatment procedures with using nanofiltration. At that time, there was a project in the European Union comparing different soil aquifer treatments coupled with aquifer recovery systems. And there was an issue, a discussion going here in Europe on what was better, if to treat first wastewater at a very high level before introducing wastewater to the aquifer and then take it out to use it as drinking purpose, as is done in the Netherlands, or if it was better to treat it partially, the water, then introduce it to the aquifer and then take it out. They invite us at the end to be part of this project, and it turns out that almost all the options, including ours with no wastewater treatment, were reaching a good result, meaning that the soil is having a very important project. Just to finish this part of the story, for Mexico City, now this water called from the Tula Valley is not only the cheapest one from all the options, but compared to potabilizing wastewater inside, people accept more easily to take water from the Tula Valley. So I think in many cases we're going to go in this to the future. But what is the importance of this real situation? That since this example has been published, there are many other examples around the world in which the wastewater, treated or not treated, that is being used to irrigate it, is infiltrated into the soil, into aquifers that are used for drinking consumption. And as you know, even if wastewater is treated, emerging pollutants are present. So we began to realize that we have a very interesting example. This is Mexico City, and all the photographs I have described you in here. It was kind of a full-scale laboratory studies going from the city to the exit of the wastewater of Mexico City, the passage through the soil, and then the recovery in different rivers and lakes. And it turns out that the Tula Valley, in there, the reuse of wastewater was planned, and we managed to have very defined different areas in the region with different time under irrigation. You can identify there 0 up to 110 years under irrigation with wastewater. So it makes a perfect full-scale laboratory study to study the transport and fate of emerging pollutants on site and compare them into the field. So we began to make studies first on wastewater to define how we were doing in terms of the different pollutants. We find different emerging pollutants in Mexico City wastewater. For some of them, we found lower concentrations during the wet seasons because of dilution, but for others, we find higher concentrations during the wet season because of the pattern of consumption. Some of these drugs are more consumed during the wet season, so we found that in higher concentrations. We found also some compounds in lower concentrations than in other countries because in Mexico we have a lower consumption of some drugs. We follow some pollutants also through irrigation canals, and we find some of them decomposing due to photolysis. And in parallel, we are doing studies to assess the impact of some photosynthesizers, such as nitrates and humic matters, and how they are playing a role in their degradation. Then we study also the content of different emerging pollutants on water sources. And in general, we found that in water sources, this is a log scale, even when we found these pollutants, they were below most of the guidelines referred in literature. But so we began to find that some of them were frequently present. The most one was carbamazepine and nonylphenol and phthalates. But for these two last, there are multiple sources. For the different water springs, we found it in a very erratic pattern. For some springs, we found some emerging pollutants, while for the others, not. And it changes from one side to another. So at that time, we also make some analysis, and as you know, most of these emerging pollutants, based on their properties, should be retained into the soil. So there were also some studies assessing the content of these pollutants in the soil. We even managed to compare, this is only one example, in two soil classes, one with 10 years under irrigation with non-treated wastewater and another with 90 years of under irrigation. We found that the different classes of soil do have an effect on their removal, but also there is an effect on the time of under irrigation. Which was most interesting is that normally you should expect that for the soils with longer years of under irrigation, the concentration retained should have been bigger, but in fact for many of these pollutants is lower because degradation occurs. And also to see how these compounds are retained in the same soil, in the same area, having different organic matter contents. Normally the upper part of the soil has a higher organic matter content, while the lower has a lower one. And we found that there was a relation between the amount of compounds retained to the organic matter content in the soil. Once again, we make an estimation on the amount of, based on the result, on the amount of these compounds that should be retained in the soil, and we found that there were some pollutants that were accumulated in the soil, but the concentration was lower than the one that we should have expected, but for some compounds. At that time, also we began to think, well, we are only looking about the content of emerging pollutants in water, in soil that is being irrigated with wastewater. So we went to look in the same area what we first called pristine soils, that is to say soils that have never been in touch with wastewater, but it turns out that these pristine soils were not pristine, that even in soils that have never been in contact, there were some emerging pollutants. And the explanation for this is that some emerging pollutants are also being, it comes from the atmospheric deposition. Mostly these are plasticizers. And we managed to track all these compounds from wastewater to different spring water sources, different type, there are springs, there are wells and dog wells. And we found that in each cases the concentrations were different, but mostly you can see in the first column how the amount found in wastewater is very high compared to the one found in the water sources, and also the content retained in the soil. So in conclusions, wastewater indeed is a source of emerging pollutants for water bodies and soils. There, the content depends on the degradation, but also on the stability and the transport mechanisms. It's very different depending on the type of soil and also on the pathway of the water. The most important mechanisms to remove is adsorption into the soil, but maybe that means that we should recommend more to discharge into the soil instead of discharging directly into water courses. Organic matter content in the soil has an effect in the removal of the soil, but also, and maybe there are some pollutants that we will be found anyway in water or in water bodies or in soil, because they are ubiquitous and the main sources is not water. These compounds end by being degraded, but this idea of degradation, it's not what we normally measure in laboratory. We never measure biodegradation under 80 years of time. And also, I make a summary of several studies, because for many of these studies we also make the comparison in laboratory, but for some compounds we have found that they behave very different of what we might expect based on these chemical or physical properties. Notably for the ethyl xylphthalate and the other one is triclosan. They do behave different. One is both were expected to remain in the soil, but we are finding these compounds in higher amounts than expected. And for instance, for carbamazepine, that we are frequently finding these compounds, and even though we manage now to remove it from water using nanofiltration, this is very costly. Maybe we should start thinking to use a different kind of compounds for the diseases that it is meant to, instead of discharging it into the water, because it is very, very expensive. And to finish, and only to explain you, this area used to be an area where the Tula civilization was there, so these are the warriors. It's very impressive because this valley using wastewater is guarded by this warrior, and we have in the right side one of the warriors saying to the others that carbamazepine can be a problem, so they need to watch out and take care and protect the population from the emerging pollutants. Thank you.